Chapter 11 is going to be our last chapter. It's about sequence and series. A sequence is a list of numbers, and a series is where we take that list of numbers and add them up. There should be a pattern to a sequence that creates this list of numbers. Today we're just going to introduce these ideas of what a sequence is and what a series is and how they're created. And then over the course of the next couple lessons, we'll look at some specific types of sequences and series. So we call the numbers in the sequences the terms. So we have a first term, a second term, a third term. And those are the numbers in the sequence. A sequence is a function whose domain is consecutive integers. So what that means is we're going to have a rule that's going to look like an equation, and we're going to plug numbers in, and that's going to create the terms of the sequence. So we're going to plug in 1, and then we'll plug in 2, and we'll plug in 3, and that will create the terms of the sequence. A finite sequence means that at some point it's going to end. An infinite sequence means it's going to go on forever and ever. So this is an example of a sequence. It's a function. It looks like an equation. And to create the terms of the sequence, what we want to do is plug in consecutive integers, it said. So we'll start with 1, and then we'll plug in 1, and we'll plug in 2, and we'll plug in 3, and so on and so forth. And this one wants us to find the first 6 answers we get by doing that. So our notation is that we're going to start by plugging in 1. That means n is 1. So a sub 1 is how we read that when it has the little 1 that's kind of lower. And that means this is our first term. So we plug in a 1, gives 2 times 1 plus 3, which is 5. Then we plug in a 2. And that gives 2 times 2 plus 3, which is 7. And then we plug in 3. 2 times 3 plus 3 is 9. And at this point, you may see a pattern, and it's okay to just continue the pattern instead of doing the arithmetic. So if we plug in 4, we expect to get 11. If we plug in 5, we would expect to get 13. And if we plug in 6, we're going to expect to get 15. It is very risky to assume a pattern after just 2 terms. So I wouldn't assume a pattern just by looking at 5 and 7, because there's a lot of ways to get from a 5 to a 7. But once you have 3 that are following a pattern, then you can go ahead and assume that pattern continues. This is a different way of defining a function of a sequence. It's once again defined in terms of n, but instead of using a sub n, this uses our f of notation. We do exactly the same thing though. We begin by plugging in 1, and f of 1 will mean first term. So if I plug in 1 up in the exponent, I get 1 minus 1, which is 0, and negative 2 to the 0 power is 1. Anything to the 0 power is 1. F of 2, we plug in a 2. So that gives me negative 2 to the first power, which is negative 2. Then we plug in a 3. So 3 minus 1 is 2, and this gives me negative 2 squared, or negative 2 times negative 2, which is positive 4. At this point, if you can see a pattern, you can just continue it. If you don't see a pattern, then just continue plugging in numbers, and you'll create the rest of your terms that way. Does anybody see the pattern here?
6.
Okay, let's try plugging in another term. 4 minus 1 is 3. Negative 2 to the power of 3 is negative 2 times negative 2 times negative 2, which is
8.
negative 8. Do we see a pattern now? They're doubling and positive negative. So what's our next one going to be? Positive 16. And what will follow that? Negative 32. Okay. So if you see a pattern, you can continue it, and if you don't see a pattern, then you just continue plugging in numbers, and that'll create the terms just fine. Questions? Go ahead and try your next 2 examples. There's one more of each type of defined sequence. All right, so here we start by plugging in 1. 6 minus 1 is 5. Plug in 2. 6 minus 2 is 4. It's probably not safe to assume a pattern. Oh, it is 5, huh? Okay. Let's try that again. 5 gives 4, 3. Probably not safe to assume a pattern yet, although you probably see one. And then if we continue, the next term will be 1. I'm counting down. I can't even count. Maybe I shouldn't assume patterns no matter what because I'm struggling here.
Please excuse this interruption. All lifers, please go to the cafeteria right now for your picture with your cap and gown.
Alright, so this is just a counting sequence. On this one, if we start by plugging in 1, 5 to the first is 5. If we plug in 2, 5 squared is 25. If we plug in 3, 5 cubed is 125. And you may see a pattern at this point that what we're doing is multiplying by 5. We get 625, and then I actually don't know, 31, 25, and 15, 625. I only know my power's up to 625. Alright, so that's how we can construct a sequence from a rule. We start by plugging in 1, and we just continue plugging in numbers until we see a pattern, and then continue the pattern on out. What we want to do now is, given a sequence, we want to describe the pattern, figure out what's going to come next, and then write a rule for the pattern. The rule for the pattern should look like these first types of problems that we had, where we could plug in numbers and create these terms. So first, when we describe it, just kind of in words, what do we see happening here? Okay, so the bottoms are multiplying by 3, and there's negative switching going on. All right, so what's going to come next? A negative. 1 over 243 is going to come next. Now, to create a rule, there's a couple of strategies that we're going to use. The first one is if we have a negative flip. The way that we're going to do that is by a negative 1 to a power of either n or n plus 1, kind of depending on whether we're starting positive or starting negative. When we're creating our rule, what we want to do is call our first term n equals 1, then n equals 2, then n equals 3, n equals 4, etc. Giving them just their place in line. This is the first thing in line, second thing in line, third thing in line, just like kind of working backwards from the first type of problem we did. So since this one starts negative, plugging in a negative 1 to just a first power would give us that negative. So for this one, our rule is going to have a negative 1 to the n power. So that's going to create that positive negative flip. So anytime that you have a sequence that's directly every other term, positive, negative, positive, negative, positive, negative, perfectly every other, it's going to come from a negative 1 to either an n or an n plus 1. So this one started negative, so I want the n. If it starts positive, then I would want to use the n plus 1. Okay. Now, we said the bottom is multiplying by 3. So what we have here is repeated multiplication. We're multiplying by 3 and multiplying by 3 and multiplying by 3 and multiplying by 3. What is the same thing as multiplying by something over and over and over? An exponent. So when we have repeated multiplication, our rule is going to have exponents. So what we have in this problem is that we have 1/3 multiplied over and over and over and over and over. So what we want to do is check and make sure this actually works for a few terms. So like if I plug in 1, I get a negative and I get 1/3. So that's good. If I plug in, say, 4, negative 1 to the 4th would be positive. So that's positive, that's good. And 1/3 to the 4th power, we can check that out, but 3 to the 4th is in fact 81. So this creates the right sequence for us. So this would be our rule. I can give you some strategies as we go through these problems, but unfortunately, one of the things about sequences in series is a lot of it comes in an ability to recognize patterns, which some people have stronger than others, and it's something that just takes practice, and it's not really like a list of here's what you do first, here's what you do second, here's what you do third. It's a skill that needs to be developed kind of over time. And I can give you, like I said, some strategies here. Here's a couple of ideas that if you see a positive negative flip, you know you're going to want that negative one to a power. And if you see repeated multiplication, you know your rule is going to have to deal with exponents. And we'll look at a couple more kind of suggestions for what we can do for rules. But being able to recognize and see a pattern in a problem isn't really something that can be taught directly. It's something that has to be worked on through experience. All right, so in this one, what is going on here?
First one's by 4, then 6, then 8.
Okay, so what we see is we add by 4, we add by 6, we add by 8. So then what would happen next? We add by 10, which gives us 30 as our next term. There's a pattern to what we're doing, but we're not doing the exact same thing every time, so this becomes trickier to come up with a rule. When we have this, one of the strategies that we're going to want to employ is factoring our terms and turning each of these into a multiplication. So instead of thinking of I was adding this and then adding this and adding this, where we're doing a pattern, but it's changing each step of the way, I want to find something consistent that I could come up with, like the 36th term of this, without having to find every term along the way. So what we're going to do is look at what multiplies to make these numbers. So 2 is 1 times 2. 6 is 2 times 3. 12, there's lots of ways to multiply and get 12, but kind of looking at what we had in the other two, I'm thinking 3 times 4 is a good option. And then 20 is 4 times 5. And now I'm seeing something develop here in these numbers. Remember, we want to name our terms according to their place in line. So that's n is 1, 6 is n is 2, 12 is n is 3, 20 is n is 4. And when we come up with our pattern, what we want to do is look at what we've noticed in relationship to n. So the first thing in each of these products, how does it relate to n? So these first numbers here, how do they relate to n? They're just n, right? 1, 2, 3, 4. So the first part of our rule is just going to be n. And we're going to multiply that by, how do the second numbers relate to that?
N plus 1.
They're 1 bigger, n plus 1. And this is our rule. So if we see a pattern to our problem, but it's not consistent, we're not doing exactly the same thing. So in the previous problem, we were multiplying the bottom by 3, by 3, by 3, by 3, by 3. We're doing exactly the same thing. Okay? If we see a pattern to what's happening, but it's not exactly the same thing, so like adding 4, adding 6, adding 8, if it's not exactly the same thing, one of our strategies is to try to break down the numbers into smaller parts. Okay? All right, so what is happening here? What about the tops? They're all 2. And the bottoms are doing what? Multiplying by 5. So from our list in an earlier problem, the next multiple is 3125. So this problem has repeated multiplication. And what did we say repeated multiplication is going to become as a rule? An exponent. So for our rule, the top is 2 all the time. Nothing's happening to the top, so we're just going to put 2 up there. On the bottom, we're multiplying by 5 over and over and over and over and over. So how would we write that as a rule?
1/5 or
5 to the n. We can double check that with some numbers in the sequence. If we say this first one is n is 1, and then 2, and then 3, and then 4. If we plug those in, then n as 1 gives 5 to the first is 5. N is 2, 5 squared gives 25, and it creates the sequence that we need. All right, what do we see happening here? We're adding 2 every time. Plus 2, plus 2, plus 2. So next, 11. So when we have repeated multiplication, we looked at examples about what to do there. Here we have repeated addition. We are adding exactly the same thing every time. So this is not like the problem that we looked at before where we added 4, 6, 8, 10. Here we're adding exactly the same thing every time. So when we are adding exactly the same thing every time, what's a faster way of saying 2 plus 2 plus 2 plus 2 plus 2? How can we kind of condense that down?
Times 2.
Multiplications. So when we have repeated addition, that's going to become a multiplication rule. This is n is 1, n is 2, n is 3, n is 4 for our terms. So we are multiplying by 2 in this problem because 2 is what we're adding. But if I just do 2 times n, does that work? If I plug in 1, do I get what I need to get? No. So what do I need to do to it to make it what I need it to be? Adding 1 is a good guess. Let's check it. Now if I plug in 2, do I get what I need? Yeah, 2 times 2 is 4 plus 1, that gives 5. If I plug in 4, do I get what I need there? 2 times 4 is 8, plus 1 is 9. So that works. We just needed to adjust where we're starting here. Okay, so anytime you have repeated addition, you are going to have a multiplication in your rule, but you may need to adjust your start by adding or subtracting to get where you need to begin. Okay? I know these are really tricky. I know they are. Seeing patterns and being able to write rules is definitely something that needs to be developed. It's not something that should just automatically click for most people. A series is when we take a sequence and we add everything up. We have some notation for this. The book calls it summation notation, which sounds fun to say. I call it sigma notation, but it looks like this. I call it sigma because that big E-looking thing is actually the Greek letter sigma. So I just call it sigma notation because that's what that letter is. There are some important features to this. I is called the index. That's why we usually use the letter I. Sometimes we still use N though, or we can really use whatever letter we want. But that's kind of the variable of our problem. The number at the bottom is our lower limit. That tells us the first thing we should plug in. So we've started every problem by just plugging in 1. But you don't have to. So this tells us where we're going to start. In this particular problem, we would start by plugging in 1. But we don't have to. We can really start it anywhere. The top number is our upper limit. That tells us the last number to plug in. And inside of there, we have our rule, like we've been creating rules. So inside of there is our rule, 3i, that creates the sequence. And then what we want to do for a series is instead of listing them out with commas, we're actually adding them all together here. That makes it look like a plus or minus. We're actually adding all those things together. So write this with summation notation. So what that means is we need our sigma. If you can't write a good sigma, that's fine. You're in good company. Mine are usually pretty decent on the first day, and then they rapidly decline. I try to do them neatly when I'm first teaching them to you, but then they become very sloppy as we move throughout here. But we get this kind of sideways Michigan M looking thing, kind of like an E. What we need in the inside is our rule. So just like we were looking at rules for the other ones, we need to find a rule here. So what are we doing term to term to term here? Adding 5. When we're adding over and over and over, what kind of a rule are we going to have? A multiplication. What are we going to multiply by? 5, because that's what we're adding. So we're going to try a rule of 5n. If we start this thing at 1, does that work? So 5 times 1 is 5. 5 times 2 is 10. 5 times 3 is 15, and it seems to work. Okay? Then, at the top of this sigma needs to go, what do we plug in last? So what would we plug in that would give us 100 as an answer? 20. If I plug in a 20 for n, that would give me 100 as an answer. So 20 goes on the top of this thing. Okay. The bottom number tells us the first thing we plug in, so what should give us the first thing in the list. The top number tells us what to plug in to get the last thing in the list. All right, here, it doesn't look like we're adding the same thing or multiplying by the same thing each time. So what we want to do is look at how do these numbers relate to their place in line. So if we start at 1, we don't have to start at 1, but when I have a choice, I usually start at 1. So if we start at 1, how are the tops of the fractions related to their place in line? It just is its place in line. So our top of our fraction is going to be n. How is the bottom of the fraction related to its place in line? It's 1 bigger. Where does this series end? It doesn't. Right? We have a plus dot 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 means this thing actually goes on forever, and the way we say forever in math is infinity. This is called an infinite series. It goes on forever and ever and ever, just a plus dot 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 with no end. So we'll go ahead and start this at 1. What are we doing each time? Adding 4, over and over and over. Repeated addition is going to become what in our rule? Multiplication. So 4 times n. Does that give us what we need, or do we need to adjust our starting place? So if I plug in 1, do I get the first thing? Yep. So we're good there. And we have a last term here because there's a plus dot 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 and then there's 100 with nothing after it. So what do I plug into my rule to get 100 out of it? 25. Alright, again, it doesn't really look like we're doing the same thing every time here in terms of multiplying or adding. I like to, if most of them are fractions, or even if like half of them are fractions, I make them all fractions, just so we're comparing the same kinds of things each time then. We're going to, once again, start at 1 and list them by their place in line, and then we want to relate the numbers in the problem to its place in line. So how does the top of the fraction relate to its place in line? It's 1 bigger than it. How does the bottom of the fraction relate to its place in line? It's the number squared. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. So the bottom is its place in line squared. Where does this series end? Infinity. It's just a plus dot 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 and then nothing, so it never ends, so we put an infinity at the top. One more kind of problem today. Here we're given our series in sigma notation, and what we want to do is actually find the sum of this series. So what we're going to do is create the list of the terms, and then a series takes that list of terms, takes the sequence, and adds them all together. So the bottom tells us what to plug in first. So we're going to start by plugging in 1. If I plug in 1, I get 2. Then we count. If I plug in 2, I get 4. If I plug in 3, I get 6. If I plug in 4, I get 8. If I plug in 5, I get 10. How do I know when I'm supposed to stop? Okay, the top number is our stop sign. When I plug in 6, I get 12, and there we stop. Okay, it's not when you get that number that you stop, because then we would have stopped a while ago. Okay, it's when you plug in that number. The bottom is the first thing you should plug in, and the top is the last thing you should plug in. And then what we want to do is just add these all together, and you can grab a calculator to add them all up together. We add them all up and we get 42, and that is the sum of this series. A sequence just lists the terms with commas. A series, we put a plus sign between them, and we want to add them up. What do I start plugging in here? 3. The bottom tells us what we plug in first. So I plug in 2 plus 3 squared gives 11. Then I'm going to plug in 4. 2 plus 4 squared is 18. 2 plus 5 squared is 27. 2 plus 6 squared is 38. And that's where we stop because we just plugged in 6. So what we want to do then is take these numbers and we want to add them up. You can grab a calculator to do your additions there. We add them all up and we get 94. Questions? What do I start plugging in this rule? 5. Where am I going to stop? 10. Okay. So we're going to plug in 5. 5 squared plus 1 is 26. Plug in 6. 6 squared plus 1 is 37. And 7 gives 50. Plug in 8 gives 65. Plug in 9 gives 82. Plug in 10 gives 101. Then we want to take those terms and add them all up. We get 361. Last one, we're going to start this one at 1. We're going to end it with 5. So 2 times 1 squared minus 1 is 1. 2 times 2 squared minus 1 is 7. 2 times 3 squared minus 1 is 17. 2 times 4 squared minus 1, 31. 2 times 5 squared minus 1, 49. Take those numbers and add them all up. And we get 105. Okay? Yeah, the problems are definitely easier when you don't have to come up with a rule yourself. It is tricky. I know it's tricky. I hope I don't give the impression that it's something that should be easy. I've been doing it for a long time. But being able to come up with a rule for a sequencer series is not an easy skill. So your assignment tonight comes from 11.1. Make sure you pay attention to the directions because some of the sets of directions ask you to do multiple things.
Taylor, please.